When we get into parametrics, there's some useful equations that that will help you when you're converting from parametric to rectangular form to know what the graphs are going to look like. So we're going to look at conic sections, and the three that we're going to look at are parabolas, circles, and ellipses. And there's one other conic section called a hyperbola, and I don't think we're going to get into that, but those are the three conic section formulas that you should be familiar with. First, we're going to start with a parabola. The parabola that you've always known is y equals ax squared plus bx plus c. And if a is positive, it opens up. If a is negative, it opens down. But there are a couple other kind of parabolas that you should also be familiar with. This looks a little blurry. See if I can focus this a little better. The other two kind of formulas are x is equal to ay squared plus by plus c. That is not the equation of a function, but it's still the equation of a parabola. And in this case, if y is squared and x isn't, if a is positive, then the parabola opens to the right, or in other words, it's a C-shaped parabola. But if a is negative, then it opens to the left, or it's a backwards C-shaped parabola. And you saw this example with the first two graphs that we did yesterday. They both were C-shaped parabolas. They were the same curve. The next conic section is a circle, and I went over that yesterday, and I think you've seen these in the past. But the circle standard form of an equation, or center radius form, is x minus h squared plus y minus k squared equals r squared. And you'll see that equation when the center is at h comma k. And the radius is equal to r. So for example, if you have an equation like x minus 3 squared plus y plus 2 squared equals 16, you know the center is at 3, negative 2, and the radius is 4. So that's really nothing new or different than what you've done over the past couple of years. The next one is an ellipse, and I mentioned this yesterday, the standard form of an ellipse. I gave you the standard form when the center was at 0, 0, but sometimes the center of an ellipse is not at 0, 0. So the standard form of an ellipse is x minus h squared, just like the circle, but then you have to divide it out by some other number squared, plus y minus k squared, just like the circle, but you divide it out by another number. A and b are not equal to each other, and that is equal to 1. So when you see an equation like that, you'll have an ellipse, the center is at hk, just like a circle, and then the a and b values, the a value is the distance between the center and the rightmost part of the ellipse. So A is the distance between the center and right side of the ellipse. and B is the distance between the center and the top or bottom portion of the ellipse. It's the distance between the center and top or bottom of the ellipse. Oh, and the A could be either the right side or the left side of the ellipse. So for example, if you see an equation like this, x minus 2 squared all over 9 plus y plus 1 squared all over 4 equals 1, then you know you have an ellipse because it's in standard form. The center is at 2 comma negative 1. The distance between the right side is 3, and the distance between the top and the center is 2. So the distance between the center and left or right, that is equal to 3, or the square root of 9. And the distance between center and top or bottom is equal to 2, or the square root of 4. So if I wanted to graph this ellipse, or make a quick sketch of this ellipse anyways, the center is at 2, negative 1. So I mark down the center. And from that center, I know I have to go right 3 and left 3. So I'll go over to 5. Here's 2. So here's the right side of the ellipse, and then I have to go to the left 3. So I go back to negative 1. And then the distance between the top and the center is 2. So from here I'll go up 2, and I'll go down 2, and that'll take me down to 2, negative 3. So then I can just make a smooth sketch of this ellipse. And hopefully you did a little bit of this in Algebra 2 last year. I have a feeling you might not have. Alright, well, if I could draw it would be a lot better. Sorry about that. So anyways, this distance right here is 3 because of this 9 underneath. You square root of 9 is 3, so you got this distance of 3. And this distance right here is 2 because the square root of 4 is 2. And like I said, the center is at 2, negative 1. So you can write an ellipse with any center in any, these are called the major and the minor axes of the ellipse, but you don't have to know that. But you should be familiar with these standard forms: parabolas, circles, and ellipses. So what does this have to do with conic sections? Well, I'm going to give you some conic sections using parametric equations. And yesterday we looked at a couple of ellipses and a circle, I believe. But there's a general format, and we're going to use our graphing calculator a little bit to see what the differences between the different parametric equations will give us as far as the conic sections go. So we'll start off with an example. Let's say x is equal to 1 plus 2 sine of theta, and let's say y is equal to negative 4 plus 3 cosine of theta. And we'll have theta go between 0 and 2 pi, like usual. And if we want to set up our xy table, we can, but it would be a little bit easier to figure out the rectangular equation of this to see what it's going to look like in terms of what we know about our standard form of the conic sections. So let's eliminate the parameter by subtracting 1 from each side and then dividing by 2, because you have to isolate the sine and then isolate the cosine. So if you take x equals 1 plus 2 sine of theta and solve it for sine of theta, you get x minus 1 all over 2 is equal to the sine of theta. And then add 4 and divide by 3, and you have y plus 4 all over 3 is equal to the cosine of theta. And now to eliminate the parameter, sine squared plus cosine squared equals 1. So putting these together, you have x minus 1 over 2 squared plus y plus 4 over 3 squared equals 1 from the Pythagorean identity. And then that simplifies down a little bit to x minus 1 squared all over 4, because you have to square both parts, and y plus 4 squared all over 9 equals 1. So I can see that's the equation of ellipse. An ellipse, the center is at -1, or +1, -4, and the distance between the left and right is 4, and the difference top and bottom, the center to the top is 3, center to the left and right is 2. Sorry. So let's graph that ellipse quickly. I ran out of room here. Camera's falling down. I can get this on camera. Or maybe if you'd like to try it on your own, that would be great too. So we have an ellipse. What did we say? The center was at 1, -4. Here's the center. And the distance from left to right is 2. And the distance top to bottom is 3. Right, here's a -4. So we can just sketch this out. Alright, here's an ellipse, but we don't know what the orientation is when we eliminate the parameter and just sketch it out like a regular rectangular equation of an ellipse. So let's see if we can figure out the orientation. So we can set up a theta, x, y table and let theta go from 0 to 2 pi, and we can step up by pi over 2 like we did yesterday. Let's see where this thing starts. So if theta is equal to 0, x is equal to 1 plus 2 sine of theta, which is 1 plus 0, which is 1. And y is equal to -4 plus 3, which is -1. So over 1, down 1. So here's the starting point right here at theta is equal to 0. And now we're going to theta equals pi over 2. So when you plug in pi over 2 into your x and y equations, you have 1 plus 2, which is 3, and -4 plus 0, which is -4. So over 3 down 4, here is when theta is equal to pi over 2. So it looks like it's going in a clockwise direction. When you plug in pi, you get 1 plus 0, which is 1, and -4 minus 3, which is -7. So just like we thought, here's theta equals 3 pi over 2. We're continuing this way. Plug in 3 pi over 2, and you have 1 minus 2, which is -1, and negative 4 plus 0, which is negative 4. So negative 1 comma negative 4 is right here. Here's theta equals 3 pi over 2. Coming up around, and then 2 pi is the same as 0, so we have 1, negative 1. So it ends up here. So this is a clockwise orientation. Let's take a look at our graphing calculator and see if we can do the same thing in the calculator. So we'll make sure that our calculator is in parametric mode, which it is, and in radian mode also. Zoom in a little bit here to the calculator. And let's see if I've got some garbage in here. So we have x equals 1 plus 2 sine. Now it's gonna have a t on there, even though our parameter is called theta. We can still have it be a t here. And then negative 4 plus 3 cosine of t. And now it's important to hit the window button, and remember the theta goes from 0 to 2 pi, so that's kind of automatic if you're in radians mode, but you can check it. If you don't have 6.28, you can do 2 pi like that. And let's step by pi over 12. We'll step by small steps, otherwise we're not going to get a very smooth ellipse. And you can play around with this t step if you want to put pi over 2, if you want to put pi over 4. Experiment with different t steps and see what the graphs are going to look like. Now the x min, let's see, the minimum x value is negative 1, so let's go back from negative 5, and we can go up to positive 8, I guess. And then the y value, the smallest y value is negative 7, so let's go down to negative 9, and we can go up to 1. And let's see what that looks like. And there's our ellipse. And if we trace around, you can see the starting point here. And if you push your right hand arrow button, you'll see that it goes in a clockwise direction or clockwise orientation. Now what I want you to do is press your y equals button, and let's see what really small change this has to our ellipse. What if we change sine to cosine and cosine to sine? Well, you can imagine that some of these values are going to change on our t table or on our theta table, but not really very much, because cosine goes between negative 1, it'll go negative 1 to 0 to positive 1 to 0, and sine will do the same thing. So let's take a look at this graph. You can see it's the same ellipse that had the center. Just like before, it had the center at 1, negative 4, and it looks like the left and right and up and down are all the same. But if you trace this around, you can see it starts over here at 3 comma negative 4, and now if you press the right hand arrow button, you can see that there's a counterclockwise orientation. Same ellipse, but it's just going in the reverse direction. So that's just something that's a little bit interesting. All right, so those are a couple of conic section examples for you, and we already did a circle example and a couple of parabolas in class or in our earlier notes. I want to show you one more thing, though, about parametric equations that's a little interesting, and that's when you get natural logarithms, or e's, that are defined as your functions of t. So let's look at natural logs and e to some function of t. All right, so this could be like e to the t, or e to the 2t, or e to the negative t, but we're going to have ln's and e to the power of something in our parametric equations. Now these natural logs and e functions have nothing to do with ellipses and circles and parabolas, or the conic sections that we looked at before. And let's see what we would do if we encountered something like this. Let's say x is equal to e to the negative 2t, and y is equal to e to the positive t for our parametric equations. And let's say t goes between, let's say -1 up to 3. So let's take a look at eliminating the parameter first before we set up our table. Okay, we're going to solve for t. To eliminate the parameter. So if you have x equals e to the negative 2t, if I wanted to solve that for t, if you remember, if you have a t in the exponent of an e base, then you can take the natural log of each side. So I'm just going to put an ln in front of both sides of this equation. So you're going to get the ln of x is equal to the ln of e to the negative 2t. And if you remember, if you take an ln of e to anything, it's almost like canceling out the ln and the e. So you're going to get ln of x is equal to negative 2t. And if you solve that for t, then you get ln of x all divided by negative 2 is equal to t. So that's solved for t. And now we're going to take that t value and put it in the y equation up here. Y equals e to the t. So if y equals e to the t from our parametric equation, then we can call that e to the ln of x over negative 2, which is the same thing as e to the negative 1/2 ln of x. I just brought the negative 2 out in front and called it negative 1/2. Well, if you have two things multiplied by each other as an exponent, then what you can do is, if you remember your rules of exponents from Algebra 2, or we mentioned them this year, we can raise this to the power of the ln of x and raise the whole thing to negative 1/2. Because if you have a power of a power, then you're multiplying exponents. And if you multiply those two exponents, you're going to get this. And why would I want to do that? Well, I'd want to do that because e to the ln of x, if you remember back to our log chapter, e to the ln of x is just equal to x. So what that is equal to is x to the negative 1/2 power, and x to the negative 1/2 power, because it's a negative exponent, it's 1 over, and x to the 1/2 is the square root of x. So that's our y value. So there's your rectangular equation, y equals 1 over the square root of x. If I wanted to set up my t-table to do this by hand, it wouldn't be a whole lot of fun, because if t is equal to -1, I would have to calculate e to the negative 2 times -1, which is e squared, and I think I remember e squared was something like 7.4. Oops. I'm sorry. That should be in my x column. And then the y value is e to the t. Well, e to the t is e to the negative 1 power, which is 1 over e, which is some crazy decimal. I don't know. I'd have to pull out my calculator. Now we have t equals 0, so we have e to the 0 and e to the 0, which is nice. e to the 0 is 1, e to the 0 is 1, so at least I've got some nice point on my curve, 1 comma 1. But then when you let t go up to 1, 2, and 3, you get some really crazy numbers. E to the negative 2, which is 1 over e squared, which I don't know what that is. You get e to the negative 4, which is 1 over e to the 4th, and e to the negative 6, which is 1 over e to the 6th power. I'd have to pull out my calculator. And then e to the 1st is just plain e squared, and e cubed. So these numbers really need to come out of our calculator, but let's just take a look at our graphing calculator, put it in parametric mode, or it already is, and let's take a look at what this graph looks like. We have x is equal to e to the negative 2t, and y is equal to e to the power of t. I'm going to change my window. T goes from negative 1 all the way up to, what did I say, 3. And let's step by 0.2, I guess would be a small enough number. And let's see if we can see this. Let's see, x max goes to, that would be good enough, and y max would be e cubed, and e cubed will probably be something 30 is probably big enough. Let's see. Alright, so it looks like we've got a curve that comes down like this, really small, and let's see if that's anything like 1 over the square root of x. So let's change the mode back to function mode, press y equals, and let's do 1 over the square root of x. And look at our graph, and it's the same exact graph as we got with the parametric, so we must be okay. Changing back to parametric mode, we can press the trace button and see what our values are when t equals negative 1, x equals about 7.4, and y was equal to 1 over e, which I guess is 0.367. And then just tracing along the way, 1, 1 was on our list, and then we can just keep on going. And the x values get very small, and the y values start to get pretty big, just like what our table told us. So those are some interesting examples of some parametric equations using some trigonometry and using some natural logs. So we'll get some practice at that tomorrow. Yay!